Okay, so regression line. Let's consider a table of data. Of course, here when we compute by hand, we shall consider very simple data table. Okay, let's consider this table, and let's find the regression line associated to this table. So y equals ax plus b. This is the fun. And our unknowns are a and b, with the condition that the under the least squares method. That means we must consider the following expression as a function of two variables a and b, which is called the least squares error. So this is actually an error, and we might minimize it. The idea is to consider the Euclidean distance between the point of coordinates given by the table and the theoretical value that we are looking for. So that is axj plus b minus yj squared, the sum of these squares. This is in general. Okay, so in our case, it is y at -1, it is minus a plus b. Y at 1, it's a plus b. And y at 2, it's 2a plus b. So it is minus a plus b. And from here we subtract the measured value. The measured value, it's minus 1.5 squares plus a plus b minus 0 squared plus 2a plus b minus 1 squared. So this is this expression, which is a function in two variables, a and b, must be minimized. So we have to apply the usual, please.
But the first one isn't plus 1.5?
Sorry, here, plus, of course. Plus, of course. Because here it's negative and we have 2 times the sign minus. Yes, very well, thank you. Okay, so now we need to compute the partial derivatives of e with respect to both variables. Sorry, here we have 2 times 2a plus b minus 1 times 2. Okay, so plus 2a plus 2b plus 8a plus 4b minus 4. equals so 12a plus 4b minus 7. Please make the computation, and finally we must check if we've got the same values. Yes, please. Now the derivative with respect to b. Okay, this is what I've got for the partial derivatives with respect to a and with respect to b. Please tell me if you got the same values.
La prima cred că este 8 în loc de 12.
E 8, da. 2. 2a plus 2a plus 2 plus 2
E 12.
plus 4 plus 8. So it is 12. It was okay. Maybe you forgot to multiply by 2 here. I don't know. So again, the first one was 12a plus 4b minus 7. And the second, I've got 4a plus 6b plus 1. Is it okay? Acolo cum ți-a dat 8?
Uitasem de minusul din fața lui ea.
Asta
Da,
de...
bine.
Okay.
Da, da.
It's okay. So now we need to solve the system 12a plus 4b minus 7 equals 0. 4a plus 6b plus 1 equals 0. Now here, when we consider the least squares method, always the system is a linear system. So a system of first degree which has usually only one solution. That solution will be what we are looking for, because we discussed at the lecture that always this will be the minimum point, actually a global minimum for the function e. So we need to compute this to solve this system. If you multiply the second equation by 3 and then we subtract them, let's try like this. Okay, let's put here equals 7. And we subtract them, we get that 14b equals minus 10. So b equals minus 5 over 7. That is b. And now if we replace b in the first equation,
N-ar fi trebuit să fie 10, 7 minus 3.
da, am scăzut din a doua pe prima, că altfel de aceea ar fi minus aici.
Da.
Okay. So now if we replace b, we get 12a minus 20 over 7 equals 7. So 12a equals 69/7. So A, we simplify by 3 here. 23. It is 23/28. Tell me if you got the same values. So our function seems to be 23/28x minus 5/7. This is the answer. Is it okay?
Da.
If you have any questions about, so this is the regression line. This is the function of first degree, whose graph is called the regression line associated to our table, and we know the properties and so on. So now if we want to make some predictions using this method, now we need to evaluate y at some other points different from -1, 1, and 2. Yes. For example, we can evaluate what will be the value of y at 3, for example, and so on. Okay, so this is a very simple but very important application, which is based on the algorithm to find the local extrema of a function of, in this case, 2 variables. Okay, now you said to consider conditional extrema. Yes. Let's consider, for example, the function f of x and y equals x squared plus y squared. And the question is to find the extreme values of the function f on the set k equals x squared plus 4y squared less or equal than 1. Okay. So we have the following problem. We have a continuous function, namely x squared plus y squared, which is defined on this set. This set is what? Now, x squared plus 4y squared equals 1. It's an ellipse, which in the canonical form can be written as x squared over 1 plus y over 1 over 2 squared equals 1. So it is an ellipse with the axis 1 and 1 over 2. It looks something like that. And the set here, it's 1. And the set on which we want to find the, attention, the extreme values of the function. So actually we are not looking for the local extrema. We must look for the extreme values of the function on this set, including on the ellipse. From the theory, we know that a continuous function on a closed and bounded set, okay, it's closed. Why is it closed? Because here we have less or equal, so it contains its border, and bounded. Okay. We know that a continuous function on a closed and bounded set always is bounded and it takes its extreme values. That means there are points in this set at which f takes its minimum value and its maximum value. Actually, we are looking for these extreme values of the function f, not necessarily the points where it takes this value. We shall find them anyway, but it's a little bit different problem. Okay, now the difficulty is given by the fact that this set is not open. On the contrary, it's closed. If it is, it would be open if here the inequality would be strictly. Because on why the fact that it is not open, it's a complication. It's a little bit more complicated because the usual algorithm which give us the local extrema cannot be applied on not open set. So the method will be the following. We shall find all the possible local extrema on this set, because obviously the extreme values of the function f will be taken by the function where? At local extrema, of course. But so the problem is that we cannot find them on the entire set K from the very beginning. So we shall split our problem into two other problems. The first problem is on the border, inside. We can also start with the other one, but usually we start inside. Inside means on the set D, which is K without its border, without the ellipse in our case, so strictly less than 1. This is an open set. And here we know how to find the local extrema. We have the usual algorithm, so we compute sorry, the partial derivatives of f we find the critical points. We have one critical point, 0, 0, which is in D. So we don't go further to decide if this point is or it is not a local extremum. Actually, it is. It is a local minimum. But we don't care about this. You will see why. Because finally, we shall compute the function, the values of the function f at every possible local extrema, and then we shall compare the values. So inside the set K, we have only one possible local extremum, this one. Now, the second problem is on the border. On the border means on the set M, actually the ellipse. Yes? Okay. Well, and this is the new kind of problem. Here we apply Lagrange multipliers method. So Lagrange multipliers method, which consists in we start by introducing the following function of 3 variables, x, y, and lambda. Lambda is a new variable called Lagrange multiplier. Okay. So here, for where it comes, the theory says if you want to find the localissima of the function f on the set given by the condition g of x, y, and 0, you must consider the function of three variables, f of x, y, and lambda, given by f plus lambda j. So you must write the condition x squared plus 4y squared plus 1 as x squared plus 4y squared minus 1 equals 0. And this is g from the theory, from the right. And now please please compute the critical, the partial derivatives of the function capital F.
Prima e doi plus 2 lambda i.
Okay, so the variables of capital F are x, y, and lambda. So there on capital F to there on x is 2x plus 2
2
lambda x. Now with respect to y,
2y plus 8y lambda.
yes. And now the last one, you can write it into ways. It is actually g, because the partial derivative of capital F with respect to lambda, it is exactly this expression, which is this. So the last equation is always g equals 0. Okay, so now we need to solve the system which gives us the critical points of the function capital F. Okay, let's solve this system. Now, from the first equation, we get x times 1 plus lambda equals 0. Then y times 1 plus 4 lambda equals 0. And of course, the last one is this one. And now, as we can see here, if we have few cases, yes? Now, if x is different from 0, sorry, if x equals 0, let's consider for this case, yes? Then the first equation is fulfilled, yes? Now, we go to the second equation. Here, if y equals 0, nu știu, sau la voi se aude așa foarte fin o muzică cumva? A tăcut, nu știu. Ok, nu știu, la mine se auzea ceva așa parcă. Ok. If both x and y are 0, in that case, the first two equations are fulfilled. But if we replace them in the last one, we get 0 equals 1, so this is impossible. So x and 0 cannot be both 0. So now, if from the first equation x is 0, then we go to the second equation, then from here y cannot be 0, so necessarily lambda must be minus 1 over 4. Yes? And now we go to the last equation and we replace x by 0 there. 4y squared equals 1. That means y equals y12 equals plus and minus 1 over 2. So we have the first solution. If lambda is minus 1 over 4, we have two possible local extrema on the border. Those are 0 and 1 over 2, and 0 and minus 1 over 2. The second case, if x is not 0 from the first equation, then necessarily lambda must be minus 1. Now we go to the second equation. Here, one of these factors must be 0, but lambda is already minus 1. So because lambda is minus 1, the factor 1 plus 4 lambda cannot be 0. Because it is 0 if lambda equals minus 1 over 4, but lambda is already minus 1. So necessarily, y must be 0. And now we replace y in the last equation. We get x squared equals 1. So we get x 3, 4, plus and minus 1. So we get, when lambda is minus 1, we get a critical points 1, 0, and minus 1, 0. So actually we have 4 points on the border and 1 point inside. Remember, it was 0, 0, yes? Where f can take its extreme values. And now all we need to do is to compute the values of the function f at this points and compare them. F of 0, 0, it's 0. Remember, f was x squared plus y squared. F of 0, 1 over 2 actually equals f of 0 minus 1 over 2, which is 1 over 2, which is 1 over 4. And f of 1, 0 equals f of minus 1. It equals by chance, not in general, this is not true, which is 1. Yes. So if we now compare the values of the function, we find that this is the minimum value of the function on our set, and this is the maximum value. So if we go back to our picture, here in the beginning, the minimum value is taken at the origin, here, 0, 0, and the maximum value is taken at 1, 0, and minus 1, 0 here. Okay. 1 and the points 0, 1 over 2 and 0 minus 1 over 2, it can be proved that they are local extrema but on the border, but they are not the points where f takes its minimum value. Its minimum value is taken on the set K at the origin. Okay, if there is any question about okay, let's see another example. Let's consider f of x and y equals x squared negative y squared. So the question is to find the extreme values of the function f on the set K, which is the closed disk of center 0 and radius 2. Okay, let's try this one. So the idea is, as in the previous example, our set, it's a closed disk of center 0 and radius 2. This is a closed and bounded set. So we shall look for the possible, to the candidates to be local extrema everywhere, and then, okay, one second, alo? Putem să vorbim mai peste după ora 10? Mulțumesc, da, ok. So, again, we shall split the problem into two. The first problem is to find the possible critical points inside. Inside means on the set D, which is given by the strict inequality x squared plus y squared strictly less than 4. This is an open set. That's why the usual algorithm to find localistima works. We know it. We start by computing the partial derivatives. And of course, there is only one critical point, 0, 0, inside, which is inside D. Okay. So again, we have one candidate inside. Now, the second problem is to consider the border, yes? Now, on the border, which means the set M, given by the equality x squared plus y squared equals 4. And here we use Lagrange multipliers method. We consider the function f, capital F, of three variables to be f of x and y plus lambda times g of x and y. Now remember, f was x squared minus y squared, and g is x squared plus y squared minus 4. So that means x squared minus y squared plus lambda g times x squared plus y squared minus 4. Now let's compute the partial derivatives of the function capital F. And the last equation is, of course, g equals 0, which means x squared plus y squared equals 4. And similarly, as before, the first equation is x times 1 plus lambda equals 0. The second equation is y times lambda minus 1 equals 0. And now again, we have something similar as before. Now, if, for example, from the first equation, lambda equals minus 1, if we replace it in the second equation, then necessarily y must be 0. And if y must be 0, By replacing it in the last equation, we get x squared plus 4, which means x equals plus minus 2. So we've got the points when lambda equals minus 1, we got 2, 0, and minus 2, 0. Similarly, from the second equation, if lambda is 1, so from the first equation, x must be 0. Because this factor cannot be 0. It is 0 when lambda is minus 1. So in this case, we get the points 0, 2, and 0, minus 2. Now, if lambda is not minus 1 and not 1, none of them, then necessarily lambda different from 1, lambda different from minus 1, then necessarily x and y must be both 0 from this equation, which is impossible because from the last equation we get 0 equals 4, which is false. So we have 5 possible points where f takes its extreme values: 0, 0, 2, 0, and minus 2, 0, 0, 2, and 0, minus 2. And now we shall compute the values of the function f at all those points and comparing them. F of 0, 0, it's 0. F is here, this one. F of 2, 0, which by chance it's f of minus 2, 0, gives us 4. F of 0 minus 2 equals f of 0, 2, gives us minus 4. And now, obviously, the maximum value of f is 4, and the minimum value of f is minus 4. So this time, the extreme values are taken on the border. At the point 0, 0, it's not important here, but the points 2 here and here, f takes its maximum value, while here and here it takes its minimum values. Its minimum value. Okay, again, if there are any questions here. If you have any question in general. Please, again, I didn't hear you.
Când o să dăm examenul, desenăm și noi elipsele sau sunt opționale?
It's optional, but it helps. If there are exercises where the picture is important, so it must be somehow be done. But I think in many cases they may be helpful. I think. Now it's your decision. In this exercise, it's not necessarily. You can avoid them, but I think they could be helpful. Okay. If you have other questions, types of exercise, or you want to take another one, the algorithm is clear. If about the algorithm you have any, I don't know. Let's consider another one. For example, let's consider f of x and y equals x squared plus y squared minus 2x plus 3y plus 5. And we want the extreme values of the function f on the set K. Let's take the closed unit disk. Okay. Now, about the picture. This is the unit disk. It's not a big deal to buy. It's okay. We can solve the exercise without any picture, if you prefer like this. So again, we shall split the problems into two. First of all, inside. So inside means on the set D given by x squared, the open unit disk, yes. Here, this is a usual problem of local extrema. We need to compute the partial derivatives of the function f. And the critical point, there is only one critical point, has the coordinates 1 minus 3 over 2, but as you can see, it is not in D. So sometimes the critical point where the critical, some of the critical points are not in our set, as you can see here. D is this one, and obviously this point doesn't satisfy the condition of D. So inside there are no candidates. The only candidates are on the border. Now on the border, that means on the set M given by the condition x squared plus y squared strictly less than 1, we must consider the function f of x, y, and lambda, which is f of x and y plus lambda g of x and y. Now f is this one, which is g of x and y. Sorry, here it's equal. I took the same equal on the border, on the circle. G is x squared plus y squared minus 1. Okay, this is the function capital F. And now we need to compute the partial derivatives of capital F. And of course, g equals 0, which means this. So from the first equation, we get that x times 1 plus lambda equals 1. And from the second equation, we get that 2y times 1 plus lambda equals minus 3. And now, if lambda is not minus 1, yes, so start with if lambda equals minus 1. Obviously, if lambda equals minus 1, the first two equations are not fulfilled, because if lambda equals minus 1, okay, let's start with this case, which is the simple one. If lambda equals minus 1, the first two equations will be 0 equals 1 and 0 equals minus 3, which is false. So, conclusion, hence, lambda cannot be minus 1. So in this case, from the first equation, we get that x is 1 over 1 plus lambda, and y is minus 3 over 2 times 1 plus lambda. And we shall replace them both in the last equation. So this time you see, actually, the value for lambda, it's important. The lambda, it's important because actually we shall find first lambda and then x and y. In the previous examples, it was not the case. So by replacing these values for x and y in the last equation, we get 1 over 1 plus lambda squared plus 9 over 4 times 1 plus lambda squared equals 1. If we consider here the same denominator, we get that 13 over 4 times 1 plus lambda squared equals 1. So I shall write here 1 plus lambda squared is 13 over 4. So 1 plus lambda is root of 13 over 2. So lambda 1 will be minus 1 plus root of 13 over 2. And similarly, 1 plus lambda equals minus this one gives us lambda 2 equals minus 1 minus root of 13 over 2. So we have two values for lambda. Okay, and now for each of them, we shall find x and y. So for lambda 1 equals minus 1 plus root of 13 over 2. X and y are given by this formula with respect to lambda. So x1 will be, in this case, 1 plus lambda is root of 13. So 1 plus lambda 1, it's root of 13 over 2. So x1 will be 2 over root of 13. And y1 will be minus 3 over 2 times root of 13 over 2, which is, so the first candidate will be 2 over root of 13 and minus 3 over root of 13. Now, if lambda equals this, the other value, minus 1 minus root of 13 over 2, in this case, 1 plus lambda will be minus root of 13 over 2. So x2 will be 1 over minus 13, square root of 13 over 2, which is negative 2 over root of 13. And y2 will be 3 over root of 13. So here we have, for lambda equals this value, we have the candidate 2y2 given by minus 2 over root of 13 and plus 3 over root of 13. So our candidates are only 2 points. Because there are only 2, we already know that, and f must take its minimum and its maximum value. We already know that at this point, f takes its extreme values. Remember, the first one, this one from here, you see, from the beginning, was not inside our set. So here it's clear that at one of these points, f takes its minimum value. At one of these points, f takes its maximum value. To decide, we compare them. We compute f of x, f of 2 over 13, negative 3 over root of 13. And by computing here, we get x squared plus y squared. It's obviously 1. Yes, attention, each time x squared plus y squared, it's 1 for many reasons. First of all, because this is the sum. It's 4 over 13 plus 9 over 13. But also, it's from the condition x squared plus y squared equals 1. Okay, 1 minus 4 over 13, root of 13, minus 9 over root of 13, plus 5, which means 6 minus root of 13. And now f of the other one is f of minus 2 over root of 13 and 3 over root of 13. That will be 1. Now it's plus root of 13 plus 9 over root of 13 plus 5. That means 6 plus root of 13. Obviously, this is the minimum value, and this is the maximum value. And the problem is, of course, solved. Okay, let's take not more than 5 minutes of break, and then we shall continue up to about 10 o'clock, yes? Okay, so